All right. I think in the previous video we talked about electric current and only electric current. Basically, that electrons flow through circuits at any given amount of time. So electric current I is equal to delta Q over T, which is basically electric current is the total charge flowing through a circuit over a given amount of time. Now, if you take a look at the circuit on this PowerPoint right now, you'll see that, well, you have a battery at the bottom, right? So there's a negative and a positive side, and the negative side has more electrons than protons. And what's going to happen is that all those electrons want to get as far away from each other as possible. And they're going to go from the bottom all the way through this wire, right, through this circuit, goes through the light bulb, lights it up, right, it powers it, and goes to the positive end, goes to the positive side. So this is basically a simple circuit. This is how electricity works. So electricity flows through a conducting wire and you get power, okay? And so everything is done using circuits. Now, let's move on. So again, let's do a brief review of current. And current is the rate of electron flow over time. So how many electrons are flowing through this wire, flowing through a circuit in a given amount of time. All right, and so we know that current is measured in amperes or A, and the variable for current is I. So again, electric current is the amount of flow of electrons in a period of time. Now let's move on to voltage. And so uh, there's something else I want to go over. You were introduced to voltage last unit, but I want to talk more about voltage because voltage is very important. Voltage is the basically how much electrons you really have. What is the total charge? What is the amount of charge you have in a given area? Not flowing through an area, not traveling through an area, but actually in any given area, right? So you can kind of think of it as water, right? When we relate a lot of these things, I'm gonna give it a lot of these analogies as relating to water. So you can think of voltage as water. And so if you have a higher pressure, if you take a look at the left-hand side, if you have a higher pressure, what's going to happen is that higher pressure water is going to flow down to the lower pressure side of things, right? So you can think of this water as electrons. So on this left hand side, there's a lot more electrons, and what's going to happen, all those electrons want to get as far away from each other as possible. So those electrons are going to go to the side where there are less electrons. So this, you can think of voltage as this way. Voltage is the amount of electrons in a given area, and this pressure difference, this potential difference, this voltage difference drives an electric current, because what's happening is that the water is now moving to the right hand side. This water current, right? There's a water current being generated, and you can think of this as electric current. So a higher voltage generates a an electric current. A higher voltage generates an electric current. That electric current moves to the lower pressure side. Okay, so again, there's a higher voltage here, forces the electrons to go to the less uh, to the lower voltage side, generating an electric current. This is also one of the reasons why voltage is most commonly referred to as potential difference, and you can kind of see it being demonstrated over here. So you have a higher potential, right, on the bottom on this GIF, right, higher potential on the bottom, or rather on the left-hand side, and because you have more electrons on the left-hand side, you're going to be forcing all the electrons to the right-hand side, which is there is lower potential. Right, so again, this is higher potential to lower potential, higher voltage, lower voltage, higher water pressure, lower water pressure, and the water is electrons. Now resistance. Let's take a look at the resistance, right? So uh most objects, you can kind of think of resistance as, well, first of all, let's start with the basics, right? If you think of a circuit, If you think of a circuit right here, you have these electrons flowing through this wire. And as they flow through this wire, they go through appliances, objects like a light bulb and lights it up. But what happens when this electric current flows through this wire is that well, rather flows through the light bulb slows down the flow of electrons. And you can kind of think of it as a dam, right? Clearly, there's a higher water pressure, a higher voltage on this side, on the top side. But as it flows through the dam, that water current decreases. If this dam wasn't here, there'd be so much water flowing, and so there'd be a much higher current. But because the dam is because the water is flowing through the dam, the water speed decreases. So the electric current decreases, and there's this resistance right here. And so even though there's a higher voltage here, this dam is slowing things down. This dam is slowing things down. So that's what you can think of as resistance. So let's relate it back to the light bulb, right? As the electrons flow through this light bulb, what the light bulb is doing is it's slowing the flow of electrons, just like this dam would slow down the flow of water, right? It's everything is being slowed down as you run it through appliances or objects. So every appliance has a resistance, and we measure resistance in ohms, okay? We measure resistance in ohms. Uh, let's take a look at this circuit again. So if you let's transit. This is basically how you're gonna see most things in regions. How they're gonna represent most objects, rather most circuits. They represent the battery as this. So there's a long side, right? And that side represents positive, and there's a smaller side. So that side usually represents negative, and so the electrons flow from the negative side, right? And so you see this arrow here, and they go to the right hand side. All right, and so we represent resistors, right? Resistors are any light bulb appliances that electrons flow through. So we call anything that electrons flow through a resistor. Right, that's what we call just what we call it, a resistor. So the electrons are flowing through this resistor, and if this switch is turned on, then electrons will flow through the wire. If it's turned off, well, then the wires don't touch and electrons don't flow. All right. Now, let's move on. So now, let's talk about Ohm's law, right? Let's talk about Ohm's law now. So this law is named after Ohm, right? And so on your reference table, it's R is equal to V over I. Now, let's talk about how to solve these problems. So number one, hold on. Let me just turn on my tablet. Should be quick. Done. Done. All right. That's much better. That's much better. That's a 1, by the way. Should I even erase it? All right, 1. So in a simple electric circuit, a 24 ohm resistor, so R is 24 ohms, right, is connected across, and again, this omega right here is ohms. And we measure resistance in ohms, omega. So it's connected across a 6-volt battery. So that's our voltage right there. So that's our voltage right here. So this is 6 volts. What's the current in this circuit? And so you know your formula for this is R is equal to V over I. Alright, so R is 24, V is 6, and I is I. Alright, so now multiply I on both sides. Get 24I is equal to 6 divided by 24. And you should get 0.25 amperes. All right, so that's how you would solve it. Number 2 looks exactly the same. Number 4 looks exactly the same as well. Potential difference again is voltage. Number 6, I believe in you guys, a 6 ohm resistor that obeys Ohm's law. Well, number 6 is simple as well. It's actually the same exact thing. So number 5, it says a 6 ohm resistor when applied decrease the current pass. So, and you're doing R is equal to V over I, right? And the resistance stays the same. And the only thing that changes in the problem it says that when the applied voltage is decreased from 12 volts to 6 volts, the current passing through the resistor does what? So R is the same, so we don't care about R. So I'm going to say R is, let's see, voltage is 12, right? So that's the first situation. Voltage is 6 now. So I. So what happens to the current if your resistance stays the same? Now your resistance is 6. It says in the problem your resistance is 6. So what happens to I when resistance stays the same and your voltage decreases? Well, let's solve this out. If you can't figure it out using just based on looking, right? Let's just solve it. So this cancels out. 6 I is 2 amperes. Well, let's not actually do that yet. Let's not do that. So I is 6I is equal to 6, and these cancels out. So you divide by 6, and I is just 1 ampere. So what happens to the current when you decrease the voltage? Well, then your current decreases as well. It becomes half, which makes sense because when you decrease the amount of voltage you have, right, you decrease the water pressure, which means that the current is going to decrease as well because you're slowing down the rate of electron flow. You don't have any as much electrons anymore. So that makes sense, all right? And so everything else should be straightforward.